Hey, today we're talking about Natural Wonders Chapter 15, which is all about stellar evolution. So when you look up at the stars in the sky, not all of those stars are the exact same thing. Stars end up changing and evolving over time, over their lifespan, and they have a lifespan, a beginning, a birth, and an end. And today we're going to be looking at all the different changes from the beginning to the end of different sized stars. While we're going through Chapter 15, please make sure that you're drawing down the diagram you're going to be seeing on the screen. That diagram is going to be really important, and it's actually going to be a big part of the quiz coming up later in the week. All stars in the sky, every single star that there has ever been, always starts with the same 3 steps. The very first step is called a nebula. And a nebula is just this big, beautiful cloud of dust and gas. And they don't produce any light, so we can't really see them because of the light they make. They don't make any light. We see them because of the light passing through this cloud. Stars beyond the nebula shine through it, and we can see it here on Earth. And when I say that nebulas are super gigantic, I mean they are huge. One nebula can be over 25 light years across. And a light year, that's the distance light can travel in 1 year. If light travels nonstop for 1 entire year, every second of every day of every week of every month for a whole year, that's 1 light year. And just to give you a little idea of the distance light can travel over time, the sun, which I think is really far away here from Earth, light travels from the sun to Earth in something like 8 minutes and 26 seconds. From the sun to Earth in only 8.5 minutes. Imagine going that same speed for an entire year, the distance that you would travel. Take that number, multiply it by 25, and that's 1 nebula. Huge. The next step that all stars go through is called a protostar. And this is when that big cloud of dust and gas, that nebula, starts to condense down into a single star. And now it starts producing its own light, just from the friction that's produced when all of this material is pulled together by gravity. They're bumping into each other, and that's friction, and it produces heat, and it produces light. So protostars, they're not quite a star yet, but this is when the majority of all of that dust and gas starts to contract to one area. After a protostar, the third step that all stars go through is called the main sequence. And this third step, the main sequence, is when we can really call it a star. There's one very important thing that takes place here, and it's in your packet, so underline it. It's nuclear fusion. Fusion with a U. So we're taking 2 small elements. We're taking hydrogen, the lightest element on the periodic table, and they are being pulled together by gravity, the gravitational pull of these stars, and they're pulled together with such force that those 2 individual atoms, they collide together, they fuse together to become something heavier. They become helium. And in that whole process, a whole lot of energy is released. So fusion is like an explosion in a star, and it is a force that presses out in all directions all the time. But the reason the star doesn't just explode as soon as fusion begins is because there's an opposing force. I'm talking about gravity. Gravity is pulling in on this star from all directions towards the center of the star. So there's this constant battle of fusion pressing out, gravity pulling in, and that's what ends up settling the surface of these stars. And that equilibrium of fusion versus gravity is something really important to understand, because we'll be talking about it with several other stages in stellar evolution. And so a main sequence star are stars that are changing hydrogen into helium. That fusion is taking place, hydrogen fusion. And the majority of all stars in the sky are main sequence stars. Something like 91 or 92% of the stars that we see in the sky are all main sequence stars. This is the longest stage by far, and it's just because hydrogens are very small. There's a lot of them, and so it takes a lot of time to fuse them into heliums. And you could almost imagine if you're starting with 100 hydrogens and they all fuse together, you would have 50 heliums left over, so half the number of atoms. And for our picture, you see that there is a picture of a main sequence star, and that star looks a lot like the sun, and yes, that's because the sun is a main sequence star. After the main sequence, there's this fork in the road. There's 2 different pathways that a star could take. One pathway is what we call the low mass stars, or small stars, and these are stars that are up to 8 times larger than the sun. So think about the sun, think about 8 times bigger, and anything less than that, those are the low mass stars I'm talking about. And then the other pathway that we'll get to in just a minute is the high mass stars. So think again, 8 times greater than the sun and bigger. So these are massive stars we're talking about here. And so the low mass stars would include the sun. So what we're going to talk about now is the projected future of the sun. What's going to happen to the sun next? And when the sun starts undergoing the next round of fusion, so it's no longer hydrogen fusion that happens in a main sequence star, now it's going to be helium fusion. So with helium fusion, you're fusing together atoms that are twice as big in this case. We're taking helium and it's colliding together with so much force that those heliums, they fuse their nucleus together and they produce carbon. And they release twice as much energy as hydrogen fusion. And so the explosion that takes place is twice as big as what was happening in the main sequence star. The gravity, the force pulling in, has stayed the same. The mass is the same. We don't gain or lose mass with these stars. So the mass, the gravity, always stays constant. The reason they can change size is because of the fusion taking place inside of them, the explosion. So now we have a much larger energy release with fusion, and so the sun's surface, the sun will do this, starts to expand very rapidly, and the star grows. The gravity pulling in stays the same. The fusion pressing out gets much more aggressive, until eventually the gravity and the fusion, they balance each other out, and the star settles on a new size. It's much larger, and we call these stars red giants. So the next step for the sun after the main sequence is a red giant, where it's really kind of expected that the surface of our sun is going to expand out to the orbit of Mars. Think about that for a second. Wonder what will happen to Earth. After a red giant, the sun will turn into a white dwarf. And that is the end stage of our sun, is a white dwarf. And this is related to that relationship between fusion and gravity. Because main sequence stars that turn into red giants, they don't have enough mass to fuse carbon. So now we're taking these carbons, they're colliding together inside of a red giant, they no longer can fuse. So that means our force pressing out completely stops. Gravity is still pulling in. So it takes this red giant star out to the orbit of Mars, and it starts to collapse very rapidly to something probably more planet-sized, and that would be our white dwarf. And there's so much gravity, there's so much force pressing these molecules together, these atoms together, that there's still a lot of friction, there's a lot of heat, and so it's a very bright color, a very hot white color, but they're just very small. And that's eventually what the sun will become. It will become a white dwarf, and then over time they cool off into a brown dwarf and a black dwarf, and then they're really just a giant diamond floating up in space. Next, if we go to the high mass stars, after main sequence, a very similar thing takes place where we're now fusing heavier and heavier elements, and this produces supergiants. But these supergiant stars don't stop at fusing carbon. The carbon can be fused into oxygen, and the oxygen into neon, and the neon into magnesium, and then from there into silicon and sulfur and argon, and then into calcium and titanium and chromium, and eventually into iron. And that's where the fusion will stop for our supergiants. And along this way, we're fusing together heavier and heavier elements, and that means the amount of fusion taking place, the energy release is going off the charts, huge. Like, the fusion's crazy. It's so large, there's so much energy output, and that is our force pressing out. So again, the gravity of these stars is also very large because there's so much mass involved. But the fusion is so great, the surface of these stars end up just gigantic. One of these supergiant stars plopped down into our solar system. The surface of the star would be out to Jupiter's orbit. It would take up most of our solar system. So these supergiant stars are just absolutely massive, and that's because they're fusing together such heavy elements, all the way up to iron. But once it gets to iron, there's no more fusion. Iron is too big of an atom to be pulled together with the gravity to fuse, so fusion stops once it hits iron. And again, there's an equilibrium here. There's the fusion pressing out and the gravity pulling in. And so when that fusion, that force pressing out stops, gravity takes over, and we have this very quick, very rapid collapse of a supergiant star. And that massive collapse ends up slamming together in the middle of the star to have one more massive round of fusion that we call a supernova, which is our next step in stellar evolution. And this supernova, it is kind of what it sounds like. It is an explosion. It's the collapse of a star that gives off tons of energy and light and ends up producing the raw material for nebulas. The outer layers of these massive stars end up getting cast off and blown off into the galaxy, and all that's left is a core. And this is where we have another fork in the road, because the two different outcomes of a star, the two different cores that remain, depend on the star's mass. For stars that are between 8 and 25 times the size of the sun, that core that remains will be a neutron star. And it's called a neutron star because it's just made out of a mass of neutrons. There's so much gravity, the density is so intense with neutron stars that it actually causes the electrons in the electron cloud of every single atom to collapse down into the nucleus with the neutrons and also the protons. And if you know anything about subatomic particles, a proton plus an electron equals a neutron. So when we force all of these electrons into the nucleus, we're really canceling out those protons, and you just have a massive core of neutrons. It's a neutron star. And for those rare stars that are greater than 25 times the size of the sun, you have a black hole. And black holes are something that we are learning about all the time. We still don't know a lot because we can't see them. Light cannot escape a black hole, so the only way we know black holes are out there is through math, where we can see their gravitational pull, and also because light is actually bent when it passes close to a black hole. They bend light. And so that would be the other outcome after a supernova, either a neutron star or a black hole. Please make sure that you have drawn out this diagram of stellar evolution. You will see it on the quiz. And if you have any questions, please make sure you ask. All right. Thanks.